When a spacecraft drops out of orbit and hits the Earth's atmosphere, it is traveling at roughly 17,000 miles per hour. At those speeds, the friction from the air alone generates enough thermal energy to instantly incinerate metal. To survive this fiery plunge, the earliest aerospace engineers in the 1950s relied on the established logic of aerodynamics. They assumed the safest vehicle shape was a long, sharp nose cone. Look at the wind tunnel testing from that era. You can see the engineering focus was entirely on these sleek, missile-like silhouettes. It made perfect sense based on what they knew. The fastest things in the sky were early supersonic jets, which relied on incredibly pointy noses to reduce air resistance and increase speed. The prevailing assumption was that the atmosphere was a thick medium you needed to slice through as cleanly as possible to minimize drag. But a spacecraft plummeting from orbit is moving at hypersonic speeds, more than 5 times the speed of sound. At that velocity, slicing through the air causes a catastrophic thermal failure. The problem with a sharp tip is that it acts exactly like a magnifying glass for heat. It takes the intense thermal energy generated by atmospheric friction and focuses it directly onto a single tiny point on the nose. Because heat is so localized, the metal tip quickly reaches its structural limit and melts away. Once the nose deforms, the carefully planned aerodynamics are ruined, and the spacecraft begins to tumble dangerously out of control. Hitting the atmosphere at 17,000 miles per hour means the air molecules simply cannot get out of the way fast enough. The gas compresses so intensely that it stops acting like normal air and behaves more like a solid, scorching wall. By trying to cleanly cut through that wall, a pointy ship invites the friction to stay in direct contact with its surface, transferring all that destructive heat straight into the vehicle's frame. To survive, engineers needed a shape that seemed completely backward. They realized the best way to enter the atmosphere was to lead with a wide, flat, and entirely unaerodynamic bottom. This counterintuitive idea, the blunt body concept, was pioneered by NASA researcher Harvey Allen. This chalkboard diagram shows his physical proof. Allen calculated that a wide, blunt face would radically alter how surrounding air behaved, creating a formation he labeled a bow shock. Instead of slipping smoothly through the air, a flat shape violently slams into it. This creates a massive cushion of incredibly dense, compressed gas. By using the air's own resistance against itself, Allen found a way to turn the immense friction of the atmosphere into a protective barrier. This cushion is the bow shock wave, and it essentially acts as an invisible force field. It forces the vast majority of the reentry heat to stay at a safe distance ahead of the spacecraft. As the superheated atmospheric gas hits the bow shock, the wide angle of the wave forces that scorching air to flow outward, making it spill out and around the sides of the vehicle rather than making direct contact. Because the hottest plasma is suspended away from the hull, a physical buffer of cooler air forms against the surface of the flat heat shield. This gap is what prevents the cabin from melting. A slicing nose cone absorbed almost all of its own frictional heat, but by slamming into the atmosphere and projecting a shockwave forward, a blunt body redirects up to 99% of that heat into the surrounding air. This single mechanical insight solved the thermal crisis of orbital return, making the blunt heat shield the most crucial safety mechanism in the history of human spaceflight. This physical reality dictated the entire look of the space race. It is exactly why the famous capsules from the Mercury, Gemini, and Apollo programs share a distinct wide-bottomed gumdrop shape. In this photograph of an Apollo command module before flight, you can see the broad, gently curved heat shield dominating the entire underside of the spacecraft. While the top of the capsule is tapered to cut through the air cleanly during the upward launch sequence, the vehicle must flip around before coming home to ensure that flat, blunt surface faces the extreme heat of reentry. This post-flight capsule shows the actual results. The heat shield is heavily scorched and charred by plasma, but the structural integrity of the blunt face remains completely intact. Without that wide, flat barrier holding the bow shock wave at bay, no crewed mission would have survived the plunge back from the moon. Decades later, this exact same fluid dynamic principle dictates modern aerospace design. From the newest SpaceX crew capsules to the heavy robotic rovers landing on Mars, they all rely on a blunt body heat shield to break through the atmosphere. Once the vehicle drops below hypersonic speeds and the thermal threat dissipates, the massive shockwave fades. Only then can the parachutes be safely deployed to gently lower the unaerodynamic capsule the rest of the way to the surface. So, while intuition tells us that speed requires a sharp point to slice through the wind, the extreme physics of spaceflight tell a different story. Sometimes the only way to survive the fall is to present a flat face and absolutely refuse to move out of the air's way.